Hello, I am Sameen Fatima. I am a professor in the Department of Computer Science and Engineering, College of Engineering, Osmania University. Today we will be talking about clustering. The outline of today's talk is as follows. The first thing we will discuss is the cluster analysis basic concepts. Following that, we will discuss two different algorithms under clustering, one hierarchical clustering and two partitioning clustering. Under hierarchical clustering, we will study two different methods, one the agglomerative method and the second is the divisive method. Under hierarchical clustering, we will also see the different intra-cluster distance measures. With these two methods, we will conclude this topic. We will now see what is cluster analysis. Cluster analysis is finding groups of objects such that the objects in a group will be similar or related to one another and different from or unrelated to the objects in other groups. Now, within a cluster, within a group, the objects that are there, their distances should be minimized. We call the distances between the objects in a group as the intra-cluster distances. Now, the intra-cluster distances have to be minimized. The other thing is, between the clusters, the distance should be maximized. The distance between the clusters is referred to as inter-cluster distance. So, inter-cluster distances have to be maximized. That is the basic goal of cluster analysis. Clustering is an unsupervised learning task because there are no predefined classes in clustering. There are many types of clustering available. In this lecture, we shall cover two different techniques for clustering, namely hierarchical clustering and partitional clustering. Hierarchical clustering is a set of nested clusters organized as a hierarchical tree, as the name suggests, such that the inter-cluster distance is maximized. In the second kind of algorithm, the partitional clustering, a single set of clusters is formed such that the intra-cluster distance is minimized, which is what we saw in the last slide. This type of clustering produces nested clusters organized as a hierarchical tree. Now, this hierarchical tree is what we call as a dendrogram. If you look at the picture, you find that we have several clusters shown on the right side. We have a small inner cluster where we are grouping objects 1 and 3 in cluster 1 and 2 and 5 in cluster 2. Later, we combine cluster 2 with the point 4 and make up a cluster 3 and so on. So, this is the hierarchy that I am talking about. If you see on the left side, the same thing is depicted in the form of a tree or what we call as a dendrogram. If you see initially 1 and 3 are combined in the tree and 2 and 5 are combined, then 2 and 5 cluster is combined with the data point 4. This group, the 2 and the 4 point, they are combined again with group 1 to form another cluster. Eventually, this big cluster, which consists of points 1, 3, 2, 5 and 4, is combined with 6. So, ultimately, we have combined all the points into one big cluster. Under hierarchical clustering, we have two different methods. One, the agglomerative approach, and the two is the divisive approach. In the agglomerative approach, if you look at the right side, you have the little algorithm or the steps. In the initialization step, we say each object is a cluster. This is a bottom-up approach. Now, if you look at the visual, you will find that each of the data objects A, B, C, D and E are put in an individual cluster, each one of them. So, we have basically 1, 2, 3, 4 and 5 clusters, each consisting of one data point. The next step, if you see on the right, is the iteration step. Here, we merge two clusters which are most similar to each other until all the objects are merged into a single cluster. So, let us do this on the left hand side. Let us go bottom up. We just formed 5 clusters each consisting of A, the next B, next C, next D, and the next one was E. At the next level, I will merge two into a cluster. A and B will together form a cluster because they are close to each other. D and E will form another cluster because they are close to each other. Then I shall combine this D cluster with the point C to form another cluster which consists of C, D, E, as you see in the visual. Then eventually I will combine the cluster having AB with the cluster having CDE into one big cluster which has all the points A, B, C, D and E. The second kind of hierarchical clustering is the divisive approach. Now let us look at the right hand side where we have the algorithm or the steps. The first step is the initialization step, in which we say all objects stay in one cluster. The divisive approach goes top down. We start with one cluster in which there are all the data objects or the data points, namely A, B, C, D and E. So this is one big cluster. In the next step, the iteration step, we select a cluster and split it into two subclusters, and we do this until each leaf cluster contains only one object. Let us do that on the left side. If I am going to split A, B, C, D, E cluster, I get two different clusters, A, B and another one C, D, E, as you can see in the visual. Then the cluster C, D, E is split into two clusters, one consisting of C alone and the other consisting of D and E. Again, we will break them further into smaller clusters. A and B will split into A cluster and B cluster, and DE will split into D cluster and E cluster. So going top down, eventually we have each data point in a single cluster. So we started off with all objects in one cluster and came to the leaf nodes where each object is in a single cluster. This is the divisive approach. Now let us see what is a dendrogram. This is a beautiful tree. Now here in hierarchical clustering, we are forming groups at different levels or different hierarchical levels. So it is not just at one level. You tell me the level that you are working at and I can tell you how many clusters are getting formed. The same thing is depicted in a dendrogram. A dendrogram is a binary tree that shows how clusters are merged or split hierarchically. Each node in the tree is a cluster. Each leaf node is a singleton cluster. Now look at this visual again. We are cutting the dendrogram at a different level. Now here, look at the level that we are cutting. If you are cutting at this level, you will find that we have three clusters now. You can see the three rounded up. The first three leaf nodes are in one group, the next four are in the second group, and the last two are in the last group. So we are forming three clusters now. Now let us see how to merge clusters. We need to answer how do we measure the distance between the clusters, which is what is called as the inter-cluster distance. And look at this visual. You have two clusters, each consisting of 4 points. Now, how do I compute the distance between these clusters? There are so many points here and there are so many points there. Which points do I choose to find the distance? Now, it is a very interesting question. Now, there are different measures that are available in the literature which define the distance between the two clusters. Let us take a look at them one by one. The first distance measure that is available for intercluster distance is the single link distance method. Now, in this method, the single link distance between two clusters is represented by the distance of the closest pair of data objects belonging to different clusters. Now, please look at this visual. 2 points, namely P in cluster Ci and Q in cluster Cj. Now, these 2 points, if I pick up from the two clusters, they are the closest when compared to the distance between any other 2 points between the cluster Ci and Cj. So, I take this to be my single link distance. Mathematically, you compute all the distances between all the points in the cluster Ci and all the points in the cluster Cj. After computing all these distances between these two cluster points, we will find the minimum distance, and that decides the single link distance. the pictorial depiction is very clear as to how the equation is being represented. The next intercluster distance computation is called as complete link distance. Now, for this, once again refer to the visual. The complete link distance between two clusters is represented by the distance of the farthest pair of data objects belonging to different clusters. If you look at this visual, you have 2 points P and Q which are farthest, one from Ci and the other from Cj. So, what we have to do here is, once again we need to compute all the distances between the points in Ci and the points in Cj. Then we have to look at the maximum distance. That distance decides the complete link distance, which is what is represented in the equation as max dpq. This P and Q can be any point in Ci and Cj respectively. The next intercluster distance computation uses the average link distance. Please take a look at the visual. The distance between two clusters is represented by the average distance of all pairs of data objects belonging to different clusters. So, what do I do here? I compute the distances between all the points between the two clusters Ci and Cj. As you can see in the visual, I have drawn all the lines. Then after taking all these distances, I shall average it out, and that average distance is going to be my average link distance. The same thing is depicted in the equation. D min is equal to average of dpq, p belonging to Ci and q belonging to Cj. The next intercluster distance is the centroid distance. Please take a look at the visual once again. The distance between two clusters now needs computation of two different quantities, one mi and two mj. Mi is the mean of the data points available in cluster Ci, and mj is the mean of all the 4 points in cluster Cj. Now, using these means, we shall compute the distance. Now, the distance between cluster Ci and Cj is represented by the distance between the means of the two clusters, namely mi and mj. So, basically we are taking the means and then taking the distance between the means, which forms the centroid distance. So, what we just saw was hierarchical clustering. Under hierarchical clustering, we saw two different approaches, the agglomerative approach and the divisive approach. We also went pictorially and we saw how it went. Agglomerative went bottom up and divisive went top down. Then we were looking at the intercluster distances. The question was that, how do I compute these intercluster distances? For doing that, we used the single link distance, the complete link distance, the average link distance and the centroid. So, this is the way we compute the distances between the two clusters. Now, with this, we will complete the discussion on hierarchical clustering and move on to the next clustering algorithm, which is the partitional clustering algorithm. Partitioning a database D of n objects into a set of k clusters such that the intra-cluster distances is minimized. Now, you see here we are having only one level of clusters. In the hierarchical clustering, we had several levels, and if you tell me the level, I can look at the dendrogram and I can give you that many clusters as you would desire. But in partitioning algorithm, we have only a set of k clusters that we can have. The k can be defined by you. Under this set of algorithms, we are going to cover the k-means algorithm. K-means is a partitional clustering algorithm. There are many such clustering algorithms. We have taken up one for a sample. In k-means clustering, each cluster is associated with a centroid or a center point. Each point is assigned to the cluster with the closest centroid. The number of clusters k, however, has to be specified by the user. So, in k-means, we are making k clusters, and for each cluster we need to designate a centroid, and then we have to put all the points that are close to the centroid in that kth cluster. Now, let us take a look at the k-means algorithm, which is a partitional algorithm. In step 1, we select k points as the centroids. So, we are given some number of points. From that, we will randomly select k points. Then, we will repeat the following 2 steps. 1. Form k clusters by assigning all points to the closest centroid. Second, recompute the centroid of each cluster after doing this. Now, you keep doing these 2 steps until you find that the centroids do not change. You will see that we are given some data points, namely 2, 4, 10, 12, 3, 20, 30, 11 and 25. These points have to be grouped into 2 clusters because k is equal to 2. So, given are the points and the number of clusters k. Now, randomly we have to assign some means. Let us take some random values. I have chosen 2 different values 3 and 4 to be the means of the 2 clusters that I want to design. So, M1 is 3, M2 is 4. Now, let us start working with the data points. The data point 2, is it close to 3 or 4? It is obviously close to 3. So, I will put this data point 2 in cluster K1. Point number 4, is it closer to 3 or 4? It is closer to 4. Hence, I will put this in cluster K2. The first point is 4. The next point 10, 10 is closer to 4, so I shall put it in cluster 2. 12 is closer to 4 than 3, so I put it in cluster K2. 3 is closer to 3, hence I put it in cluster K1. The next point 20 falls under cluster K2 because it is closer to 4. So, also 30, 11 and 25 fall in cluster K2. So, you see in the third line K1 consists of 2 and 3, K2 consists of 4, 10, 12, 20, 30, 11 and 25. Now, I need to compute the centroids, the new centroids for these 2 clusters. For K1, the centroid of 2 and 3 is 2.5 and the centroid for K2, which consists of 0.4, 10, 12, 20, 30, 11 and 25, the centroid is 16. So, my M2 becomes 16. So, I shall start once again iterating through this process with M1 as 2.5 and M2 as 16. Once again, in the next row, you will see that I am putting the data points which are given to us, namely 2, 4, 10, 12, 3, 20, 30, 11 and 25 into clusters based on these 2 new means M1 2.5 and M2 16. Now, again point 2 will fall under K1, point 4 will fall under K1 because they are all close to 2.5 rather than 16, and you will also see that there is one more point in the middle of this given data 3 which will also fall under K1 because all these 3 are closer to 2.5, whereas the remaining points 10, 12, 20, 30, 11 and 25 are closer to 16 rather than 2.5. So, I put them in the second cluster K2 and the list is shown in the 4th bullet. Now, I have to repeat this process. What do? I again compute the centroid for K1 cluster, which consists of 2, 3, 4. The centroid for that is 3, therefore, M1 is equal to 3. And for the second cluster, if you take the mean or the centroid, M2 is equal to 18. Now, I have again a new set of means. With this new set of means or centroids, I will once again reorganize my clusters, which means I have to go back to my given data, compute the distance between that value and the 2 centroids M1 and M2, and then put them in the appropriate cluster. So, you will notice now that the point 10 has shifted from cluster K2 to cluster K1. K1 has grown to 4 points 2, 3, 4, 10 and cluster K2 has 12, 20, 30, 11 and 25. Again find the centroids. M1 becomes 4.75 and M2 becomes 19.6. Now, with this new centroids, I will again form the new clusters. Now, you see I am going on doing this. How long should I go on doing this? I should go on doing this until my elements in the clusters do not change. So, K1 is equal to 2, 3, 4. Now, with 4.75 M1 and M2 19.6, I have a new set of clusters 2, 3, 4, 10, 11, 12 and K1 and 20, 30, 25 in K2. Now, K1 consists of all these points and the mean for that is 7, and K2 consists of points 20, 30, 25, the mean of which is 25. Now, if you repeat this in the next step, you can check that K1 and K2, if they are not changing, then you can stop this iteration. You have to stop as soon as the clusters with these means are the same. So, that means in the iteration step n minus 1 and step n, the clusters K1 and K2 do not change. That means the elements in the two clusters will not change. We have seen all through that the elements in the clusters are changing. So, we went on doing this algorithm repeatedly. So, we shall continue this till a point where K1 and K2, the elements, they do not change anymore and they remain in their own respective clusters. Now, the question is, where do we stop this algorithm? This algorithm stops when the cluster means do not change anymore, which means that the data elements in each of these clusters do not change from one iteration to the next iteration. So, let us summarize this whole lesson. Today, we discussed the topic clustering. Clustering is an unsupervised learning technique. In an unsupervised learning technique, we do not have any class information. Under this clustering task, we first set out our goal. Our goal was to minimize the intra-cluster distances, that is, all the points in a cluster, the distance between those points should be minimal. And the second goal was to maximize the inter-cluster distance. So, between the two clusters, the distance should be maximized. That was the goal we started off with. Then we discussed two different algorithms, namely the hierarchical clustering algorithm and the partitional clustering algorithm. Under the hierarchical clustering algorithm, we discussed two approaches, the agglomerative approach and the divisive approach. Under hierarchical clustering, we also took a look at dendrograms and their role. Under hierarchical clustering, we also discussed some inter-cluster distance measures, namely single link, complete link, average link and centroid. The second method that we discussed was the partitioning algorithm, and under this algorithm, we formed different clusters at just one level. Under this, we covered one particular algorithm, the K-means algorithm. We have several algorithms in clustering, and every day, believe me, newer and newer algorithms are being added to clustering. So, this is not the end for clustering, but there are many more techniques and many more applications for clustering. Thank you.